So maybe if we are still waiting for them for a couple minutes, like, do you guys have any questions? Like, she just mentioned something like installing stuff. Yeah, yes. I see you're using Windows, right? Or like, yes. So for Mac, yeah, I guess it's more or less like Linux environment. Also, like you may want to have a sandbox somehow. So try to learn virtual environment. So when yeah, I can just this thing. So actually, when you install Anaconda, it's more or less a virtual environment also. But yeah, another option is you just install Anaconda. So Anaconda, but I don't know what hyphen. Yeah. So and you basically you don't, yeah, as I mentioned to her, you probably don't want to mess with like your system OS that much, especially if that is your only machine there. Maybe you need that for some other assignment, and suddenly you just spend like a couple of days just want to see like why your computer is not working or something like that. That would be pretty bad. So okay, I guess I would just get started. So basically what we left last time, I guess yeah, I'm not sure like you guys realize that I can't recording this as screencast. I guess maybe that's the reasons that the other guys realize that, and so they realize they don't really need to come anymore. Okay, I have this advertisement, but drop this first. So okay, last time we started and stopped talking about linear regression, and just to review a little bit. So remember, like when we do machine learning, it's all about generalization, and let me use red color. It's better. And we talk about high bias and high variance. So this is some kind of jargon you probably want to know. People talk a lot about that. And we mentioned about regularization. So what we are going to do today, we'll look into like classification. So last time we talked about a regression, right? This time we talk about linear classification. So basically, like, okay, the difference is now for classification, you have kind of your output is discrete. So it's like several different classes or different labels. So for example, you have an image, you want to recognize what kind of object is that. You want to say, okay, this is a cat or this is a dog or something like that. So, okay, like last time, we can have an input. Let's say if it's an image, I can have an image vectorized into a vector, a column vector. And if I use a linear classifier, for example, it will be like this. So I have a very tiny image. Let's say I have 2 by 2, just a patch. So, and I will just vectorize it. And also, like, I will pad a 1 there from convenience. As last time, if I pad a 1 here, this basically just an offset, right? So, but if I add that, then I can just write everything into a simple, like, vector product or like inner product, just X transpose multiplied by this W here. And W is the weight that we want to find, such that we can use that to recognize the object. So let's say if we are just doing a binary classification here, So the only thing we want to say is just whether the image is a cat or not. So we want to adjust this W such that when it's a cat, so then this X transpose multiplied by W will be bigger than equal to 0. Otherwise, we will say it's not a cat. So then we have a basically that XW itself is like in general is we call it a scoring function. So here actually it's not yet. Actually the scoring function is H X transpose W. I'm sorry. The H here is a step function here. So basically I have ht is equal to 1 when t is bigger than equal to 0 and is equal to 0 if it's less than 0. So and then when this result f xw is equal to 1, we say it's a cat. Otherwise we say it's not a cat. So basically we just kind of rewrite this condition here, this decide if like X transpose W is less than or equal to 0 into another form with this H function here. And so, and with that, the scoring function will say the outcome is a cat when it's equal to 1 and 0 otherwise. So note that like this is exactly what people refer to as perceptron. So perceptron is nothing but it's just a linear model with a step function kind of as the activation function, or like you have a kind of hard threshold transition. And it's kind of difficult to train because as you can see later on, because this H function, the Heaviside step function, is not kind of differentiable, and also it's not continuous, so we cannot find the gradient, we cannot propagate back, and so on. So therefore, like one solution for that is like people will use a kind of smooth out this Heaviside function by a sigmoid function or a logistic function. So it's basically given by this one here. It's 1 over 1 plus exponential minus t. So basically what you see here, when I have t goes to infinity, then this will be equal to 0, right? So then this st will go to 1. So let's say this is t here. So at infinity it goes to 1. When it's equal to 0, then it's like 1/2. And when t is equal to minus infinity, then this whole thing will be infinity, then it goes to 0. So it'll be more or less something like that. So it is kind of nice because you can interpret the range here, st is like from 0 to 1. You can kind of interpret this as like probability. So you can just consider the outcome from this f here just as a probability. So it's like previously we were saying that like, okay, it's bigger than 1, then it's a cat. If less than, if it's 1, then it's a cat. If it's 0, then it's not a cat. But instead, we can say this fxw itself will give, output a probability of how likely the outcome is a cat. So, so yeah, here we just mentioned that. So the one advantage is basically is a probability. We can easily, it's conveniently can be interpreted as a probability. And then the loss function. So did I define the loss function yet? No, I didn't. Yeah. We can define a loss function. As you will see later on, it's actually a cost entropy. You will see why it's a cost entropy. So, but the loss function is defined like this. It's simply when it's a cat, when the image is a cat, then it will be equal to minus, the image really, that's the ground truth. If the image actually is a cat, then the loss function is equal to minus log this fxw, or the minus log the scoring function. Otherwise, I will say it's minus log 1 minus this. But of course, this is P, right? So this is P, right? So intuitively, when the image is actually a cat, then I expect that I want the output to say in high probability that is really a cat, right? So I hope that P is close to 1. And if P is close to 1, then log P will be approximately 0, minus log P will be approximately 0. So that would be nice. So, and if the image, the ground truth image is not a cat, then I hope that 1 minus P will be small. So again, I would expect that, 1 minus P should be big, or P should be small. Then, therefore, these things will be small as well. So, okay, intuitively, this definition of the loss function does make sense. So, any questions about that? Actually, yeah. So, so we can extend what we just discussed into multi-class classification problem. So the only thing is instead of having a logistic regression at the end, we'll just use a Softmax function. So what it does is something like this. So what we have is for example, I have 3 different classes. It can be, this image can be a cat, can be a dog, can be a sheep. So, and then I have the input as previously, let's say, just assume here is only 4 pixels. I can vectorize the whole thing. And then I multiply this by this matrix here. So basically the first row multiplied by this guy will return the score, for whether it's a cat or not. So basically, if the value is higher, then it's more likely it will be a cat. And then similarly, the second row multiplied by this guy will say whether this is a dog, and this multiplied by this guy will say whether this is a sheep. Okay, I should point to this guy first. So this number, if it's more positive, then it's more likely to be in that class. Then afterward, we want to kind of normalize these numbers into probabilities. So we want to make that these 3 numbers sum up to be 1. So therefore, this exactly, just the Softmax function is just a normalization step, such that you convert these numbers into something act like probabilities. So, and okay, and this Softmax, it's hard for me to pronounce. I will just denote it with this sigma I here. With sec y sigma, sigma I. Basically, I have this as sigma 1, sigma 2, sigma 1, sigma 2, sigma 3, something like that. So, for example, okay, maybe I give an example. What I mean is the sigma 1 will be exponential of this guy over exponential of this guy plus this exponential of this guy plus exponential of this guy. Okay, and as I mentioned already, and this output score, eventually the eventual output score can be estimated as the probability, or can be interpreted as the probability. So how about how do we judge the performance? Again, we want to look into the loss function, right? We want to define a loss function. Remember that the whole picture is always like that. So we have some training data, and when we plug into that, we can for given parameters, the current parameters, we have the output generated from the model, and then we'll compare that with the expected output, and we compare this with some kind of loss function, right? And the whole process, the whole procedure is just we want to tune this parameter w such that this loss function is as small as possible. We'll define the loss function like this. So let's say, because the output here is probability, right? So we can think of this whole things, the whole output vectors as a probability distribution. So like this. So let's say I have output like this. I have say this number is 0.7, 0.2, 0.1. So, and this is self-contributed distribution, right? If I consider these three numbers together. And then let's say the actual image, the ground truth is actually a dog. So I can think of this information as another distribution, but it's like a delta function. The distribution will be really sharp. So it will be equal to 1 at the location that's saying it's a dog, and for other places it will be just 0. Then what we can do is we say how good of our output comparing with our input will be simply comparing these two distributions, right? And the classic way to do that is it's using the KL divergence. It's defined like this. So basically, if you have two distributions, let's say I have Q is a distribution, and I have P as a distribution, I can define the KL divergence like this, basically this function here. So it's like Q log Q over P, sum over all these components here. So any questions here? Are the notation clear? So wait a sec. Wait a sec. Oops. I don't think it's my final version here. Let me go back. Any questions or just the homework? Okay. So let's make sure this is the one. Yes, I think this is the one. Any questions, or are you guys still worrying about homework? Okay. For the KL divergence, okay, as defined in the previous slide, you can easily show that like this has to be non-negative. So for example, if I consider this, I write like, okay, this is the definition, right? So I can flip this is log function, I can flip P over Q as Q over P, so I put a minus sign here. Then this log base 2, but I can convert that into lateral log. Then know that we have a very simple inequality. Basically, if I consider this curve here is y equal to log x, and this is y equal to x minus 1, you can easily see that like this this curve is always above this one. So therefore, like x minus 1 will be bigger than equal to log x. And moreover, like you see that they will only touch at one point, basically when x equal to 1. So therefore, this log x will be less than equal to x minus 1 equal to less than, this is minus sign here. Therefore, log this guy minus log this guy will be bigger than equal to minus this guy minus 1. And then you cancel this pi here, and then you get this like sum over pi, sum over qi, and both of them are distribution, so sum up to 1, so I get 1 minus 1, I got cancelled, so it's equal to 0. And also know that like this equality holds only when only when like this is equal to 1, right? qi over pi is equal to 1. So that means that like I will have like for each I, qi equal to pi, that's essentially saying that the two distribution is exactly the same. So you will have the KL divergence will be bigger than equal to 0, and only when the two distributions are identical, they will be this KL divergence will be equal to 0. So therefore, like this KL divergence, you can just think of it as some kind of distance measure between these two distributions, but it's basically quote-unquote because very precisely mathematically it's not exactly a measure, because if you consider a distance measure, then it has to be symmetric. For example, you think of like distance between 2 points, the distance between A and B has to be equal to the distance between B and A. But in this case, it's not. So if you can simply verify from the definition. Apparently, because remember the definition is like that. So if I have like KL divergence between Q and P, I will have QI log QI over PI. Apparently, these two guys will be completely different. But still, like it's because it's easy to manipulate. Like KL divergence is used in many places, and as I mentioned, like we will use this to kind of compute the loss function here. So we have the output is P, right? And we have Q is the ground truth there. So we'll just say the loss function defined as the KL divergence between these two distributions. And if we look at, if I further expand that, like this guy will be equal to this, these two sum, right? And let's see if I think and by the way, like this thing, the first term is called the entropy. You may have you probably will learn that if you're interested in the information theory class. And the second one is called the cost entropy. But because like QI is a delta, the distribution is like it is equal to 1 only at one place, right? So it's basically a delta function, right? Distribution. So therefore, like this entropy will be equal to 0, because if you sum over all these terms here, for all basically the QIs will either be equal to 0 or 1. So if equal to 0, then this guy will be equal to 0, right? If QI is equal to 1, this guy will be equal to 0, right? So either case, the whole sum will be equal to 0. So therefore, like the entropy will be equal to 0 for this guy. So I only have the cost entropy left. So that's why people keep saying, okay, we use the cost entropy loss function. That's why that's the cost entropy loss function. And again, I can simplify a little bit further, because as just mentioned, QI is just a delta function there. So let's say JX is the ground truth there, the true category there. So then I can write like this, and I can, further. So it doesn't matter really. So, and that's the cost entropy loss function. And of course, we are describing the cost entropy loss function just for one input data. So in practice, you have many training data, right? So, but it will be very simple. The total loss will be just sum over all the losses there. So you have like 100 data samples, and then you compare all this LWX, then the loss, overall loss will be just the total loss. And then of course, we need to do this optimization, right? Now what we want is we have this LW, so we want to tune this W such that this thing is small. So we just want to optimize this LW, basically. In what we described last time, we talked about linear regression and rich regression. For those cases, we have closed form solution, so it's very simple. But in this case here, in general, like, there's no closed form solution. What we can do is just rely on steepest descent. So it's very simple idea. Let's say you start with one particular W there, so this is like the W space. So think of it, if it's 2D, like the W space, I say 2D. So you start with some point there, then you just go for the slope, right? So you want to, okay, sorry, this is minimized, right? Maybe I want to draw like this. So I start from here, and then like, I will just like compute the gradient at that point, and then just go for the steeper descent. So, and keep doing that until we go to the, some local optimum maybe. And then, of course, I need to find the gradient. So as you can see here, I will modify W each time by this delta W, and delta W is basically just proportional to the gradient. And this epsilon is a learning rate there. So if you don't want to say too small and also too big. If it's too small, it will take forever. If it's too big, you will get your training algorithm will getting unstable. So, but we'll talk a little bit more later on. So first, let's compute this gradient. So it's a little bit math here. So recall that I have this LW is equal to this guy here. Sum over all this loss function for each x, and this LWX is basically this guy here. So this is the, remember, this is basically the cost entropy again. So this is the output, the score, and then this is the ground truth distribution. And then now let's take the gradient for this guy. So let's focus, like, yeah, of course, like the gradient function is like linear, so we can just have the operator get into the sum. So let's focus on this guy first, and we can write this as, okay, this is basically this guy here, right? I dropped this x here just for clarity, and I also write this wx as O here. And now I can just do chain rule, right? So let's say if I take a partial derivative with respect to wi and j. Okay, remember, like, the w is a matrix, right? So we want to see like how each of these parameters changes. So when you say take the gradient of with respect to w, actually you are really taking the partial derivative with respect to each of the element. So let's say I take just particular element, the ith j element, then I will have, okay, it's equal to this guy here, right? So and with the chain rule here, I can first take the partial derivative with respect to O. Okay, O itself is a vector, right? So I need to take care of, like, so each of this, yeah, it's something like that. Like I have let's see how I yeah, something like I have this L is in terms of O1x and O2x, right? Let's say if I just have like k is equal to 2, or like only have two different O's here, the O only have a dimension of 2, let's say, Then if I take partial derivative with respect to x, I need to take L, take O1, and take O1 x plus L O2 and O2 xy. So therefore I have a sum here. It's sum over all these O components there. And then of course I have, okay, this is this guy here. I draw a better arrow here. And this is this guy here. Yeah, sorry, the x is W, basically, yeah, let me use W again. Let's say W. Then, okay, and for this guy here, it's very simple, right? So, you're looking at the ij element of W multiplied by this x here. It will be only kind of related to, okay, which terms here will appear in this sum here. So it will only appear at the j element of x, right? So therefore this guy here will just come out with xj here. Then we need to deal with this guy. So for this guy, we let's see. Yeah, we call that, okay, O is Wx again. And and also like sigma, don't forget about it. The sigma is my softmax function. So it's this exponential O j over sum over exponential OK here. So it's easy to verify this. Okay, so do you agree that it's easy to verify this? So yeah, yeah, it's very simple, but I guess the notation just get kind of a little bit hard to read. But let me just try one of them. Let's say for this guy here, so I take partial derivative with OI. Let's say so this with OI. So if okay, this okay, sigma j here is basically exponential OJ over sum over K exponential OK, right? So if I take partial derivative with OI here, this doesn't relate to this guy, right? So it's a constant to him. This guy here, in this sum, one of the term will be I, right? So therefore, like, if I take, okay, this will be a constant, I can pull it out, it doesn't matter. But this guy here will be equal to 1 over sum over K exponential OK here square, right? Because this is like 1 plus x over y, take partial derivative of x, something similar to that, right? So if I take derivative of this, I have x plus y square, and then take derivative again, inside will have nothing, basically. So actually it's very similar to this. So I take this, I have 1 over just this square here. But then if you look at that, compare this guy, I can pull out oh, okay, I'm sorry, I forget. So it's exponential, right? So therefore, like, I need to differentiate this guy again, and this guy will give me exponential OI, right? So what I mean is, like, if you have exponential of x plus exponential of y, you take partial derivative over x, you get back an exponential of x, something like that, right? So therefore, there's an exponential OI coming up here. And then, so therefore, you have this square here, this get one of this term here, so I have basically two sum here. and this over this guy is equal to just sigma j o, right? And this will be just equal to sigma I o, right? And when I take this, actually I forget that should be a minus sign in front. When I take partial derivative with this guy, I should have minus 1 over x plus y squared. So therefore we have this one here. And you can do something similar for this guy also. And therefore, then, therefore, if I take partial derivative of this guy here, I have, I'm getting lost. Oh yeah, if I take partial derivative with respect to this guy here, okay, this is a constant, pull out, then this will be 1 over, yeah, when you're getting old, you cannot even do algebra. So yeah, anyway, like, any problem with that? So actually, I just did it like this morning. Now I don't know what I'm writing. But here, let's see why I'm writing like this. I split this, okay. Oh yeah. I'm sleep. I guess I'm really tired. So we just did it, right? Because we need to treat it differently when when we're taking partial derivative with respect to like sigma j and sigma I with respect to sigma I. Oh, sorry, this is O. I mean, this notation is so confusing. With OI, these two values are not the same. So this guy, when I is not equal to j, it's just minus sigma I and sigma j. But when it's these two i's are the same, I have sigma I over and 1 minus sigma I, something like. So I need to consider these two differently. So I just consider two different terms here. One is when like L is not equal to I, then I will use this equation. I got this. And when L is equal to I use this equation. I got this. Okay, that's it. Okay, I don't know why I was confused. Yes. So then this got cancelled. This got cancelled. So we just have Qi, and this can absorb back to here. Right? I have Qi sigma I here, and this is missing one term, right? So I can put it back. So it's sum over all L here. Sum over L Q L sigma I here. And then this really nice thing, because Q is a distribution, right? Don't forget about it. This is a distribution, therefore we sum up to 1. And this is basically just a constant to this L, right? It doesn't depend on L. If I put it out, so this just disappear. So therefore it's just Qi minus sigma I. So it's very nice. And so then back to what we have previously. Ultimately, we want to compute the loss with respect to each of the parameters W, right? So previously we used the chain rule, and we have one component here, this xj, and then we have another component. I want to make sure I didn't have any mistake here. This Yeah, okay, this should be correct, I think. So, actually I didn't mention, I mean, I skipped it quickly, but this is like, delta function also, like this is only have, okay, for each of these OK, the, OK is basically equal to W, the kth column multiplied by this X, right? Sorry, the kth row multiplied by this X. And when this row is not equal to the ith row, then this will not depend on Wij, right? So therefore, like, the only terms that OK is non-zero will be when K is equal to I. So therefore, this sum will only have one term is non-zero. So it only have one term is I. So therefore, this guy, when it's also when it's equal to I, it will simply, I have, this is OI is equal to WI something, the whole row there multiplied by X, something like, or maybe I wait, or will be equal to WI L XL some over L, right? And then the only term that is here, again, like, because I'm taking partial derivative with respect to this Wij here, the only term will be non-zero, will be when L is equal to J. So the only thing left is Xj. So then, therefore, this whole thing is Xj with this partial derivative here. And then we did that in this line here is equal to this. So therefore, the final result is simply this. So it's very simple, but it's kind of tedious, as you can see. But luckily, we will only do once like this, because eventually you find that, like, for modern day network, we always write it as some kind of like so-called computational graph. And you'll see probably in next class or the class afterward. Then you can split into very tiny kind of like small pieces. And when you do so-called backpropagation algorithm, it's just like propagating this gradient it will be it can be computed much easier than like what I did here. So I guess this probably the only class with the most algebra. Afterward probably will have much fewer like this. So and then like we have this gradient now, so we can do the steeper descent as we mentioned earlier. So in practice, if you're of course the best for the best scenario will be you use up all the training data to compute the p size LW and compute the gradient precisely. Given all your data, but maybe you just have many training data. Maybe you have like 1 million or like 1 billion data points. So it becomes very computationally intensive to compute this LW. If we want to compute all this LWX and sum them all together, so we can cheat. So basically, we don't exactly want to need to compute all of them. So you can imagine maybe I don't really have that much data, so I will just use some of the data. So therefore, like, what we can do is like we just use a small batch, maybe each time, like, and we can pick them randomly. And this is known as the mini batch gradient descent. So each time you have all this data, but you only use part of the data to compute your gradient for the loss function and to update your W. And to the extreme case, you may just pick one of them. Of course, this is not really very desirable. You just, out of all the data points, you pick only one and approximate your loss function or approximate your gradient. Formally, it's known as the stochastic gradient descent, but typically in practice, like, nobody uses it, but they keep saying that they're using stochastic gradient descent, but actually they're referring to this mini batch instead. So really, they're doing the mini batch, but people typically say stochastic gradient descent, but to be precise, the stochastic gradient descent really the extreme case. And also, like even you have a very exact gradient, sometimes it may not be the perfect solution to do steeper descent. So this is one example. If you have your your function is kind of skew, is that how you call it? I don't know. In one dimension, then you will just become quite inefficient to do gradient descent this way, because as you can see, like if I start from here, I try to descend, the best direction will be this way here, right? But your minimum is really here. So you will still get there, but you will get many steps. Maybe you move to here, then you go back like that, and like this with many hops until you get to the optimum. So some simple solution is to introduce some momentum. So basically, like you don't discard your previous gradient completely. For example, your gradient is going this way, right? So you have this component here, and then next time you go this way. So you add up this component, two components, then it kind of cancel. It will kind of smooth out a little bit, like more like this. So this is one possible simple solution for that. We'll talk more about that like later on also, but here just give a one very simple solution just mentioned here. And also, as I mentioned, like in practice, previously I said that like luckily you typically don't need to really compute all this gradient analytically. So even though you are like me, is losing my ability to compute, do this calculus thing, but you are fine. Basically, like the program will take care of that. Like many packages, they will find the gradient and actually many of them they even have the the gradient computed, but they can also like approximate numerically, like even though like maybe you don't have this kind of symbolic packages that compute the gradient like exactly, but you can do it numerically. For example, I have this W like this, and I can approximate, for example, like how I changes with respect to this weight W by simply like this way. I have this final loss function like this one, so I tilt this this term here a little bit. I kind of like perturb it a little bit by small h, and I see like how does it change compared with the original m over h. So then this is exactly the approximation, the approximate derivative, right? And this is also useful to debugging your program. Maybe you, like me, do not always like compute this kind of calculus correctly, like it sometimes gets stuck. Then you can use this just to verify your result is correct or not, right? And actually like packages Fiano, actually many packages now will compute the gradient for you. So we just can become more lazier and lazier. Okay, what I'm doing in time, I always like, okay, yeah. So conclusion, a semi-conclusion, I would say. For classification, we can fit the output. Okay, here we talk about only linear regression. Linear classifier, and we look at two examples. Two different cases. Like only two classes. We just have this final output kind of scoring function, the final step of the scoring function using logistic function, and this method is typically known as logistic regression. It's confusing at the beginning, especially like when I first learned it, like several years ago, like regression, and I would think of like regression, but it's not really meaning regression. It's really it's for classification. So, but the name is kind of stuck when it first introduced. because you are really kind of fitting curve, right? So it's kind of regression, but then you are really solving a classification problem. And for multiclass, if your scoring function utilizes Softmax function, then it's a Softmax classifier. And so find the optimum way, we do the optimization, then we can do it analytically, or like we can do it numerically. And either way, we need to rely on some kind of optimizer. So, yeah, but we'll talk more about that like later on, actually, a couple more classes. So any questions for now? It's really quiet. Actually, it sounds like I'm really talking to myself. It's okay. Yeah, I'm used to talking to myself. So I prepared a couple slides for SVM also, because it's really very much related to linear classifier. So how many of you like use SVM before? You guys must not do any machine learning stuff before, like. Okay. So it's a really famous method, especially late 90s until maybe several years ago, maybe 2000, I don't know. Still very useful. I mean, like still, people still using it, like especially when they don't have many data, like use it a lot. Very robust algorithm. And a very simple idea also. So it's still a linear classifier like this one. So you have like data at one side, for example, like this is not cat, this is cat. And this is the feature space. Basically, just say I have two-dimensional features. Then you want to find the boundary. If you do a linear classifier, you want to find the boundary. So the way to find the boundary is I want to maximize this margin. So for example, if I find a boundary like this, and I kind of see like touching these two guys here, like this point here, and this distance, this gap will be smaller than this gap, right? So I want to kind of maximize, kind of rotate this line, this plane here in general, such that the gap will be as big as possible. So it's very intuitive reason, right? I mean, it's basically it's lateral, right? Why I won't do that, like, yeah. And yeah, I really don't know why people take that long to find, discover this, but yeah, for any reason. Anyway, so, and then like, and basically, the boundary that like, the gap, let's say I have this maximum gap, and the gap that those points here touching this boundary here is known as the support vector. And that's why this algorithm is called the support vector machine. And then now, if I, for example, if I look at this gap here, and for each of this plane here, or in this case just line here, it will be described by this function here, right? This is basically okay, this is vector. It's hard to see. This is dot product between two vectors, or I may write like as transpose as usual. And this is some kind of offset. So I can always scale it such that like the other side is equal to -1, 0, and 1, right? So you are fine with that, right? So then let's say I find the equation like this. Now I want to find out how big is this gap. And the size of this gap will be, if you remember some of this geometry. So for any point on this line x here, or like how do I say that? Okay, this will be the w vector. Because if you think of that, like, let's say if I normalize this vector as like W hat, so W hat is simply this like W over the norm of that. If you remember, like if I have a vector like X dot W hat, what is that? It will just be the projection to W hat, right? So for example, if I have a vector here, let's say I have, okay, I probably should start with an origin. So if I have vector here, so I have a W here, W. So if I have vector here, let's say this is X, then X dot this W hat will just give the projection to this W hat, and it will be just equal to basically the distance between this point here, X here, from the projected point of origin to this line here, or like I should say, it's just equal to this distance, right? Yes. So therefore, like then this equation makes sense, right? For this equation, what does it mean is simply like I pick any X here. So let's just verify this equation makes sense. Any X here, projected by this W, if I do a dot product here, should have the same value, right? As you can see, like W times this X should be the same. And this is exactly what I have here. And moreover, like for any point, moreover, the distance between these two guys, therefore, will be like, if I pick one X here and pick one X here, let's say this is called X1, this is called X minus 1. The distance will be simply, X1 dot with W hat minus X minus 1 dot with W hat, right? And this will be the distance. And, because W hat is simply equal to W over W, and I know that like X1 line on this guy satisfy this equation, X minus 1 line of this guy satisfy this equation. Therefore, like Wx1 is equal to 1 plus B. So this is equal to actually 1 plus B, and this is equal to minus 1 plus B. So therefore, what I get is equal to 2 over W, right? So therefore, okay, I know how far is these two guys. It's just simply 2 over W. And so therefore, the SVM is again like just an optimization problem such that I want to maximize this gap is 2 over W, and subjected to the constraint that like I want to make sure all these points will be cut beyond this gap here, right? So let's say for the points here, I will have label like it's Y1, it's equal to Y. Y is basically the output will be okay. I mean each of the point will have an output denoted by Y, and for these points here we'll have Y equal to 1, and for the points here will be Y equal to minus 1. So therefore, either case, this guy Y multiplied by this thing here should always bigger than equal to 1, right? So because like for these points here, this will be bigger than equal to 1, and for this guy here, this value will be less than equal to 1, and but this is equal to minus 1. Therefore, like I have minus multiplied by minus will be positive, so this will be always equal to 1. So okay, then okay. You guys, okay. So yeah, and that is the equation for the SVM. And equivalently, I can also like maximizing that is equal to minimizing that. And what I just described is a hard constraint SVM that I do not allow any points to fall into the gap. But sometimes you have outlier, right? You have noise. So it may be too strict to say, okay, I don't allow anything to fall into that. So what we can do is like we can convert that into a soft constraint problem instead. Then we will have something like known as a hinge loss. What happened is like, okay, hinge loss is defined like that, mass COC. So it's called hinge, I guess probably it has a shape, something like that. Therefore it's called hinge. So we will want to minimize the, instead of like, having this to be satisfied always, we will just say, we want this to be as small as possible. So again, this will be equal to either when this guy basically is bigger than equal to 0, then I'm thinking whether I shift the I need to check the sign. Maybe I should 1 minus this guy instead. So if it's satisfied, so anyway, what I want is it's satisfied, then this guy will be equal to 0. When it's not satisfied, then this will be some positive values. So then I can rewrite my optimization problem with this hinge loss plus again, I'm minimizing the W, but typically we will minimize the W square, the 2 norm instead. And this is about the hinge loss. And for multi-class SVM, it will be very much similar. So if we have more than one classes, again, we will have each class, the score, we will first have a kind of intermediate score will be basically have the weight multiplied by your input. So have different weights for different class. And then like for this intermediate score, we'll hope that like if it's for the true class, then the intermediate score will be bigger. So let's say the true class in this case is J. Then what we hope for is that we want to have Sj is bigger than all the other the score of all the other classes. And we also add a kind of a margin here, like delta here. Just want to make sure that it's not just bigger than SL, but it's bigger than SL by some margin. And then afterward, we use the hinge loss again. So in the sense, if it's bigger than that, then there will be no loss. If it doesn't satisfy, it will be just equal to that loss. And then again, we can just incorporate that into the SVM, then we have this. So, and in practice, we have basically 2 different kind of scoring function. I mean, either you can use the Softmax, as we earlier mentioned, or like we can also use the hinge loss as for the neural network. So if you build a neural network, or like actually when you say SVM is basically just a single layer neural network with a hinge loss. But you can of course extend that, like for any neural network, you can have multiple layer, and at the end you have a hinge loss. You have a mixed model, it's kind of like SVM, but not exactly SVM. But you can also, like, instead of using hinge loss, you can use just use Softmax function as shown previously. This is kind of, I don't know, there's no one way the other is better or worse. It depends on problem. We may discuss it more later on. So this is basically all I have. I'm doing well with time, I guess this time. But actually one thing I want to say, but I don't have all the guys here. But as I mentioned, like I expect you guys to look into packages and each of you do a presentation on that. I think this is the best way to learn the packages. And tentatively, we'll have the start of presentation around mid-February. I guess I will probably use Tuesday, preserve Tuesday as for presentation. Maybe I will have like a long lecture on Thursday. And I will need your preference given to me by next Thursday. So you need to just give me names at this moment. Like just give me names of 3 packages with sorted order by next Thursday. So then I may do a small lottery. So basically, if all of you picking TensorFlow, for example, then unfortunately, I guess that would be too much if like 10 guys are talking about TensorFlow. Then I would just like kind of massage the data a little bit. I will show how I massage it. I won't do it myself. It will be random. And after and afterward, like after we decide like what you guys will present, I will basically the order will be like we'll have the most popular packages will be presented first, and then with the package also we will kind of randomly decide who is going to speak first and so on. And afterward, after we kind of decide like who is going to speak what, then I will give you all the names. I expect you guys to coordinate among yourself. Hopefully, like we don't have too much overlapping. So we all want to learn something, right? If all of you like talk about the same thing, then it's kind of meaningless. So, but a little bit overlapping is acceptable. So presentation will be 20 to 40 minutes. So maybe 30 minutes or something. Do not need to drag too long. So we expect maybe like 2 presentations per lecture. And if you guys don't mind, I will take the tape you guys. So whether you want to put it on the YouTube or not, it's up to you. But I guess it's good like at least tape it, because like afterward like we can share among ourselves. Right? I always find it very useful that like especially like even I learn something, I just don't remember it like 2 months later on. But I'm always the best teacher to myself. I cannot find anyone teach me better than I do myself. I think it's the same for you guys, because it's just wired that way, right? Your brain, you expect the things is presented that way to yourself, and then when you say it, you all think that you're speaking the most logical way. So therefore, no other teacher will teach better than you yourself. And many times when I record something, and for example, the SVM, actually, I rewatch what I said like many years ago. So it just helped a lot. So actually, I recommend you to do the same thing, like for learning other things. Like it's very useful. And so to give you guys some incentive, I will have 4 bonus awards. So basically it will be like 2 according to my taste and 2 basically according to popular vote from you guys. And the top prize will be 5%, and then the first runner up will be like 3%. And what else? Okay, this is a list of some of the packages, some suggestions. I updated this list just this morning, and watch this video lecture from CS231N. So I watched. This is like I think like the class is, I forgot, it's like last winter or like last spring. But in any sense, things just changed very quickly, because I watched another video that they did like just a year ago. Just changed quickly. Basically, just a year ago, like many packages, dominant packages are from academia. For example, you have Fiano, and you have Torch and Cafe are all from academia. But now, like the leading packages, many are from industry, like TensorFlow, and also PyTorch is by Facebook, and Cafe 2 also by Facebook. And we have MXNet. It's less popular, but it's by Amazon, and Microsoft also have something. But I didn't look into that. And there's also one from Baidu, is like Paddle. And so I recommend you take a look at that video lecture, and maybe browse a little bit and decide like what you want to do. And that's about it. And final reminder, like you have assignment and also this package selection by next Thursday. So any questions? No, then see you next week. Okay. Yeah. Oh. Yes. You may need to speak up. Press that and speak up. Oh, I will see, like, you can give me the name first. I will take a look. If you look for something like really, I would say, not many people use, I will kind of discourage you not to use it because, it's not very helpful. I mean, like, to you yourself also, think of like you go to industry in the future, you learn some particular packages that no one is going to use. It's not very useful. Yeah. Yeah. So, okay. Actually, this list more or less cover almost most. Yeah, maybe you will encounter some others, but I think the others are pretty small. Yeah. Okay. So I will see you guys next week.